And these guys are characterized by different throat coloration. And so something I've been interested in quite some time is looking at visual signals and how visual signals evolve and the processes involved in visual signals and how they can actually drive things like speciation. And so things like poison frogs are really classic in some of my introductory work. We have a lot of other signaling traits in other species such as guppies, we have butterflies. We have these really wide patterns, really intricate displays in coloration and pattern. And the processes that lead to these can give us really interesting insights into evolution in general. These traits can also be directed by different sources of natural selection and sexual selection. We have crypsis, where natural selection really can drive cryptic evolution. Here's an example of a species that we're really looking at here, the side-blotched lizard on a lava flow. You can also have an alternative where you have evolution and natural selection driving more conspicuous colorations for things like warning coloration. These same traits and same signals can also be involved in sexual selection, like the case we'll be talking about here, where things like mate choice and female preferences can drive in one direction. You can also have male-male conflict, which can act on these same type of signals. And so these signals are really involved in quite a few processes and can lead to isolation between populations. And I'm making a case in a current review paper where these visual signals are actually really kind of classic and excellent textbook example where you can look and measure divergence in traits and these visual signaling traits and see how natural and sexual selection act on them and can lead to rapid isolation across the speciation continuum. And so in this case, what we're going to be looking at with this species is one that's fairly well known and fairly common in the western part of the US with a wide distribution with several subspecies. In my sampling, I've come to know that pretty much everyone's familiar with them in their backyards, which is really nice when you're going and sampling. But males have this kind of males and females have slightly different color patterns. Females particularly have a little bit more divergence in the patterns. Males tend to have, both sexes have these, the side-blotched, which is the common name, the side-blotched lizards. And males and females both have polymorphic throat signals as well. So it's a nicely widely distributed species with quite a bit of background known of them. Probably the best known for playing this game of the rock, paper, scissors, where different male phenotypes and these throat signals are involved, heritable traits, and they're involved with behavioral correlates. So you have one morph that's a dominant morph that beats out this, a secondary morph, which is a territory guarder, but is beat out by a dominant. The territory, though, is beating out a small kind of sneaker male, which the sneaker male is beating out the larger dominant male, and so you have this kind of evolutionary stable strategy with fluctuating phenotypes between these guys. And so this is something you might have been familiar with for quite some time, where you're real familiar with these three distinct different phenotypes. So in sampling these guys, I've noticed one thing which kind of jumped out at me for quite some time is the amount of variance that you see between individuals, within populations, between populations. And so I picked a couple images here on the top of kind of this, the orange, the yellow, and the blue morphs. But I embarrassingly sometimes have issues telling apart things like some of the orange and the yellow morphs. And so one thing, coupling with this is 30 individuals from one population, just so you can see differences between females here and here, some of the males. So like I said, you see a lot of variance within populations, between populations. And as I was sampling, we've got about 500 of these guys that will be in this talk. But we noticed some morphs where you have these kind of light yellow ones, but are mainly gray, sometimes kind of hard to distinguish. You have other ones where you have color elements that are interspersed, kind of a yellow coloration in between with some of this blue coloration, and even individuals where you have all three colors in one individual. So with this, it kind of led me to the question of starting to ask, what is a morph? Is a morph always a morph? How discrete may these things be? Because they're supposedly heritable, they're very likely involved in all these behavioral correlates. So I wanted to start kind of digging apart and seeing how discrete these things may be. So with this first data set, we've got about 450 individuals in it, sampled throughout their entire range of all subspecies and all geographic areas. And we've been collecting a lot of habitat and environmental data with it. We're taking full spectrum photographs. The first part of what I'll be talking about is just using spectral reflectances. And so what I did just to kind of satisfy myself and ask, how discrete maybe are these morphs, is I took some of the regions. So the outside part of the throat can be a different coloration from the inside part of the throat. So I took two reflectances from the outside and kind of the most discrete looking areas when you look at these different guys. And then the inside, I took 3 different points, looked at them and averaged them. I also took downwelling irradiance from one site just in case there's environmental variation. I picked a really characteristic site in a broad desert, really bright lighting, no filtration through forest trees, anything like that. And we don't know, honestly, anything right now about the vision for the side-blotched lizard. So I took two species which we know can discriminate color well, the tetrachromatic species. They're also not particularly closely related. So what I wanted to do is just kind of throw it and see if, how discrete these morphs may be through two different viewers that we know can discriminate color well, and then just see how discrete these morphs may be by plotting them. So we use visual models taking into account relevant environmental data as well with the photoreceptors of two different species. And so the first comparison was to start looking at these outside colorations. And so these are, what we see is, so we plotted on these Cartesian coordinates, the XYZ planes, basically the distance between two of these different dots is the perceived differences or how discrete too many individuals or 2 points may be. What we find so far is that we find a lot of clumping between these different morphs, between the different colors. So you do see some extremes, but a lot of this looks to be some kind of continuous variation. And that's kind of something that you may expect looking at a bunch of these. And like I said, honestly, I have issues sometimes telling them apart. So these are color-coded by phenotype based on consensus between 2 or 3 individuals. When we're sampling them, we all say, hey, what does this look like to you? And then take consensus. I've eliminated all individuals, so there's about 40 of them where we just couldn't agree. We weren't exactly sure what they are, so I've taken those out. So what you see here are ones that we could fairly confidently assign to one of these 3 morphs. So with the outside coloration, again, we're finding basically the same thing between 2 visual systems for 2 things that are not particularly closely related, but we do have nice evidence that they should be able to discriminate color well. So if these morphs were discrete, we would expect them to have some spatial spread at least between them. Looking at the inside coloration, we see the same thing. And again, if you look really closely at some of these, you see some of the different colored scales next to each other where you have 2 different colors. With a spectrophotometer, I got as close as I could and really got discrete color patches. And looking at the reflectance, I know I'm capturing that particular color element that I wanted to look at in each one of those regions. So in a first pass looking at these, it seems that there's quite a bit of overlap between these 3 morphs. And again, these morphs have behavioral attributes to them. They should be very important. They should be discrete. So I wanted to look then and just do another quick pass and say, okay, look, in some of these populations we have morph reductions. So there's 3 morphs in many populations, but other populations have a loss of 1 morph and there's only 2. So I would predict that in populations with 2 morphs, having those 2, you would predict them to be more discrete or more spread from one another if they have these behavioral correlates. So if they're indeed behaviorally different and interacting with one another to identify the appropriate morph or another individual that you're looking at, you would expect them to be more discrete. But again, here we have quite a bit of spread between the morphs, quite a bit of overlap, and these I even showed some of the uncertainty. It's colored as gray. And in the trimorphic areas, we see the same thing. We see quite a bit of spread between these. And again, this is in the perception, in this case in the null sagri and the brown null. And so looking at these is kind of giving us a first pass at, well, could these things, how discrete are they? Can we get a first pass? But again, we're really not sure how Buddha can see themselves. So thus far, using the available cone models from 2 different species, again, I'm emphasizing they're known to discriminate coloration well. They don't seem to be spreading. They don't appear to be these unique discrete morphs. There seems to be quite a bit of overlap, but again, this is a preliminary pass. So some of these individuals may indeed be intermediate. So we have these behavioral differences, but as far as quantifying the coloration, a bunch of these guys seem to fall kind of between one another, and there may be quite a bit of variance in the signal, which I think is really interesting to look at. But again, we don't really know anything about OODA-specific vision yet, and so we just have begun looking at that. And so the next part of this study is we were measuring the angular resolution for them. So I picked a population that was as close as possible to the Los Baños site, the really classic example where a lot of the literature of rock, paper, scissors game has been explained. It's about 19 miles away, so distinct, but as close as I could to an area where we know that this game is going on, where we have these frequencies that are alternating over years. And so what we wanted to do is take a first crack at the vision and say, okay, well, how well can these guys see? How well can they discriminate? For example, at what kind of distance can they resolve and get some of this information from these color signals? So the first thing we just finished a couple days ago was calculating the angular resolution. And for this, it's very similar to an eye exam, like when you're taking it at the eye doctor. What's the minimum resolvable size that you can see at a fixed distance? And so we built one of the most fabulous optomotor rigs ever constructed out of various artifacts I could find around the house and the highest quality motors and camera gear. So there's more than half a roll of Gorilla Tape in this. But we built something that hadn't been done so far, and we're really pumped about this. So basically what you have is you have a ring that circles around the lizard. You have various grading sizes. You start with a wider grading size and shrink down, and it spins around the lizard. The lizard will have an innate response when it can discriminate between two bands. They'll actually track. We didn't know how it was going to go. Some species, for example, this has been done in quite a few zebrafish and some rodents. A lot of times you just get an eye response with just kind of a ticking. We ended up getting really lucky that they have this kind of exaggerated head bob, so it's really satisfying to watch their head track around. So we have this spinning rig around it where the lizard is placed at a fixed distance from the grate. The grating is fixed size, which we rotate through. And so it stares and it's restrained. We made a little restraint. You guys are notorious that they just close their eyes whenever they're stressed. So there's a lot of trial and error. We start with the wider grating size. So one cycle with these guys is one combination of white and black. Started with a wide cycling size, progressively move down and down until we break their resolution. So when they can't track anymore, they'll have, like I said, that satisfying kind of head bobbing. And when you break the resolution, they just sit and stare kind of awkwardly. So we go through these grading sizes, they move, we have this nice head tracking. When we break it, then we go back and then make sure that we have this nice positive control that we can have them respond to another grading size or to a big positive control bar. So we went through all of these and got really lucky. The lizards actually tire really fast, but with a couple of modifications, we were actually able to resolve this and got a 1.209 degree maximum resolution for this with an average of about just over 1 cycles per degree. So the equivalent of that is kind of if you took 2 pencil lines or 3 pencil lines and a little space between and then spun that around and about 2 feet away from you, that's about what they can see, and that's where they're starting to break their resolution. They've got quite good vision, and you would expect that for a small species that's eating on small insects. But this is, again, giving us a first pass. How much can they see at what kind of distances, and when can they get this information from these signals? And we were also really lucky that it just so happened to fall within a range that's just recently been published and confirmed for these brown anoles. So we have this kind of correlate where we can get an idea of, knowing what we know about brown anoles, we can build off this and build off what we're taking with these signals. So we're falling in a nice range. We're starting to figure out what these guys can resolve. We're starting to resolve what kind of information is contained within these visual signals and how discrete they may be between them. And we've got some really interesting stuff that's coming up next. I don't want to take you guys away from your lunchtime. But we also have a giant data set I've been taking for quite some time, which involves visible photographs and ultraviolet photographs where we make multispectral images. We have them available for every angle of the lizard. We've also been taking it with microhabitats. So we can start doing really interesting comparisons, looking at broad-scale divergence in the signaling traits themselves, but also measure things like crypsis. We can do pattern analysis with these, and we have the exact microhabitat under the same conditions, so we can compare where they're found across the entire distribution of these guys. We're beginning to sequence the photoreceptors for these guys, and so we'll have a much better idea then as well. So we have a behavioral correlate to go with the genetic correlate and have a better idea of how they're able to resolve and get information from these signals. So preliminary right now, but in a very short time, I think we're going to have a much better picture of what's going on with these guys in a system that I feel is so well studied, hearing about it for so long, but with so much exciting range still to kind of dig in and find out some more fine-scale information. So I don't want to take too much of your time. I just want to thank a bunch of folks who come out with us, a bunch of undergraduate and graduate students in our lab. Merced Hot Springs has been really kind to us during an incredible heat wave. They provided us and my collaborator with a lot of San Pellegrinos, and we really appreciate that. But I'd be more than happy to take any questions, or if you want to come up to me afterwards, I don't want to keep folks. But thank you so much for your attention.